All right, let's get started. I'm very happy to introduce our speaker, our visitor today, David Hernández-Uribe. He was an undergrad at UNAM, Mexico. I'm actually going to tell you the dates because they're impressive. So he got his undergrad degree in 2015. He then got a master's degree at Central Washington University in 2017. They have a very impressive petrology tectonics program there. PhD in 2020 from Colorado School of Mines, working with Richard Palin. Then a postdoc at the University of Michigan, and he's now at the University of Illinois, Chicago as an assistant professor. He's done so many interesting things. It's one of the people whose papers are like, well, that's interesting, and that's interesting, and that's interesting. It's everything from Archean continental crust to early plate tectonics, and then a major research effort on subduction metamorphism and various geochemical, petrologic, and tectonic aspects of subduction. So yeah, when I was thinking about who would be interesting to invite this year, he was at the top of my list. And so I'm really thrilled that he's here visiting us, and that many of you are taking the time to meet with him. So I will hand it over to David to talk about subduction.
Let's see how this works. Okay, can you listen to me? Yes. Yeah, thank you very much, Donna, for the words and for the introduction. So today I will be talking about different large-scale, global-scale processes that occur on our planet, on Earth. But I will be talking about them from a metamorphic petrology perspective. So particularly, I will be relating processes like long-term water cycling on Earth in subduction zones. And I'm going to be relating that with subduction zone metamorphism. And also, I will be talking about how we can study earthquakes by studying metamorphic reactions. So let's see how this works. I'll do it with my fingers. There you go. So the main two questions that I want you to keep in your head and think during this talk is, what is important of subduction on Earth? Why do we care about this tectonic process? And the other is, what is the role of metamorphism? Mineral reaction changes as a function of changes in pressure and temperature. So what is the role of that process in global scale processes, large scale processes? But before talking about subduction on Earth, let's take a step back and let's take a look to the Earth. So the Earth is unique in the solar system because it is the only planet where plate tectonics operate. So here we have that in our planet, the outermost rigid portion of it is broken in rigid plates, what we call tectonic plates. So those tectonic plates flow over a geologic time over the asthenosphere. Now we can have different type of plate boundaries on Earth between those different tectonic plates. So here I am showing a map that I borrowed from the USGS, where we can find the 3 different type of boundaries. So in green, we have the divergent margins. So essentially we have the 2 plates, one is moving away from the other one, and we have the generation of new oceanic crust. A great example, the one that we always think about, is the Mid-Atlantic Ridge. Another type of boundary that we have that is shown in gray is a transformant or lateral boundary. So here we have, as the name say it, the lateral movement between 2 different plates. We don't have the generation of a new plate or the destruction of one, just like lateral movement. And then in red, there you go. In red, we have the 3rd type of plate boundary that are convergent margins. So here we have that one plane is moving against the other plate, and then one subducts deep into the mantle. Now, I think that type of boundary is by far one of the most interesting ones, and is the type of boundary that I will be talking today. So here I am showing a cartoon of a generic cross-section of a subduction zone. So in gray, I am showing the oceanic crust that has a basaltic composition, generally has a thin layer of sediments, then we have the basalts, and then the gabbros. Now, in darker purple, I am showing the sub-oceanic lithospheric mantle, ultramafic composition. And here we have that the oceanic crust is being created at mid-ocean ridges by the decompression of the mantle, so generates basalts. Now, what is particularly important for this talk is the fact that eventually that oceanic crust that is being created at mid-ocean reaches begin to travel all the way until it subducts. Now, when it subducts, it begins to metamorphosis. That means that the oceanic crust, the basalts, begin to react as a function of changes in pressure and temperature. And then we have the generation of new mineral assemblages. Now, what is also really important about subduction zone metamorphism is that most of those mineral reactions that occur as pressure and temperature increases is that we have a lot of fluids being released. Now, that type of fluids, depending at what depths they are released, some of those will be aqueous fluids, whereas at greater PT conditions, in some subduction zones, we can have the generation of melts. So essentially, the oceanic plate is melting. Now, that dichotomy between aqueous fluids and slab melts is really important for the Earth's chemical budget because certain trace elements partition better to aqueous fluids versus slab melts, and also the other way around. So the fact that in some subduction zones we will have more slab melts, that is important for what type of trace elements we can concentrate in the mantle wedge. Now, another consequence of metamorphism is that we have, as I was saying before, the dehydration. So those fluids will be traveling to the mantle wedge. They are going to lower the melting point of the mantle, and we are going to have the generation of volcanic arcs. Now, that is really important for Earth because they pose an important human hazard, right? Like we have volcanoes in the Pacific Northwest, and understanding how they form is important for humanity. Now, another great example of why we should care about processes in subduction zones is the generation of earthquakes. So we can have, as I am showing here in orange, that earthquakes can occur at the trench. So people call these megathrust earthquake. However, at greater depths, depths greater than 20 kilometers or so, we can also have other type of earthquakes, intraslab earthquakes or intermediate depth earthquakes, that they occur as a response of fluid release associated with subduction zone metamorphism. So again, understanding these mineral reactions that led to fluid release in subduction zones will tell us, or can potentially tell us, where earthquakes can potentially happen in different types of subduction zones. Now, also we care about subduction zones because metamorphism and fluid release also controls the formation of a specific type of ore deposits. And now that is really important for us because they represent the largest endowments of specific critical metals and elements. For example, orogenic gold, they only occur in convergent margins, and orogenic gold deposits form because of the fluid release associated with subduction zone metamorphism. Now, another type of systems or deposit systems that are really important that are related with subduction zones is the porphyry and epithermal deposit system. So porphyry deposits are really important for humanity because that's the type of the deposit where 60% of the world's copper come from. Now, copper is really important for electronics, electricity, and also is going to be really important for the transition to green energy. So understanding the formation, what controls the formation of porphyry copper deposits is key for us as humanity. Oh. So now I'm going to be talking about really briefly for how we can see these on Earth. So usually people, when talk about subduction zones, they talk about the Pacific Northwest, Cascadia, other people talk about Japan. Because I am from Mexico, I will be talking about the example of Mexico. So here, Mexico is in below in the south part of the border of the United States. Hopefully you know that. Now we have that here, the Caucasus plate is subducting beneath the North America plate. And we have here in purple, I am showing the Trans-Mexican volcanic belt that cross most of our country. And then just for reference, the white star shows Mexico City. That's one of the most beautiful cities in the world. So now here, I am showing how the volcanic arc looks in Mexico City. So here in the left, you can see the city. And then in the back, you can see the Popocatépetl volcano making eruption. So showing, throwing all those ashes down to the city. And this is relatively common, has been common, like these process eruptions from the Popocatépetl have occurred in the last years. I remember when I was a kid, there was several like explosions that you can actually see on night. So that was really cool. And then in the right, I am showing both of the biggest volcanoes, again, Popocatépetl, but towards the left, Iztaccíhuatl. So now Iztaccíhuatl is not active, but then in the front, you can see at least 5 cinder cones in the middle of the city. So you can see how understanding where volcanic arcs form is important for us, for humans. Now, another example is how that same subduction zone in Guerrero, that is again, Cocos subducting beneath North America, we have the location of several ore deposits that represent the largest mines of gold in Mexico. So that is called the Guerrero Gold Belt. In yellow, I am showing different stars of different mines that again is controlled by subduction zone metamorphism. And then in the right is just a picture of a mine. Now, another example that is cool, but at the same time is really sad, is how seismicity affects people in Mexico City. So these 2 pictures were taken in 2017 as a consequence of the Puebla-Morelos earthquake. So these pictures are from Mexico City. So even though Mexico City is like 30 and 50 kilometers far from the coast, we also feel the earthquakes and get affected by the earthquakes because of the location and the type of soil that we have. So again, like understanding how seismicity occurs, what triggers an earthquake can potentially help us to understand hazards. So this picture in the right was taken like 2 blocks from where I grew up. So yeah, it's really impressive and sad. So again, so I think so far I've made several points of why subduction zone metamorphism is really important. However, there are still many questions that are focus of intensive research recently. Some of those 2 questions are at what exact depths does the volatilization, meaning fluid, aqueous fluids and slab melt release occurs on subduction zones. Another question is what is the actual role of the thermal structure of a subduction zone on controlling those depths? And when I say thermal structure, I am referring if a subduction zone is relatively cold or a warm subduction zone. So that will have an important effect of where fluids are released and therefore on the potential location of the volcanic arc, the location of the earthquakes, also the location of the ore deposits that will potentially form. Now, I will not be talking about those 2. I will be talking about the last point, that is what is the interplay, the relation between subduction zone metamorphism and other global scale processes. As I was saying in the introduction, particularly, I will be talking about long-term geochemical recycling, mass recycling, how rocks recycle deep into the mantle and how they carry water and how that change through time. And then the other one is what we can learn from earthquakes using metamorphic rocks. So how we can study subduction zones? So there's 2 ways, or at least I think there's 2 ways that we can study subduction zones processes. One is go to the field and study exterior portions of the lithosphere that subducted deep into the mantle. So again, so we know that basalts form in the mid-ocean ridge, and they transform to blue schist, and then eventually they transform to eclogites. Now I can go to the field, look to these rocks, and study different processes that occur in subduction zones by studying the rock record. So that's me in Baja California, Mexico, in a tectonic melange. So again, many people used to interpret tectonic melanges as analogs of the slab mantle interface. So this is a block within the serpentinitic melange. Or we can also study processes that occur in coherent terrains and can tell us some information about processes that occur in the slab. Now, we can also use indirect evidence to study subduction zone processes. So the way that I study subduction zone processes by using indirect evidence is using a technique that is called petrological modeling, that essentially lies in thermodynamics and we can predict what are the minerals that will form at different pressure and temperature conditions for a given whole rock composition. And then we can extract information, for example, the proportions of the minerals or how much water is being released, and then use that information to say something about different processes that occur in subduction zones. So I'm going to be dividing the rest of the talk in two different parts. Again, part one is going to be talking about mass cycling in subduction zones. So deep water mass transfer in subduction zones occur due to the subduction of the oceanic crust and the metamorphism from basalts to blue schist to eclogite facies rocks. Now, I'm going to be particularly talking about lawsonite eclogites. So essentially, a simplified way to think about fluid release in subduction zone is that blue schists are typically hydrous rocks because they have glaucophan, that is a hydrous amphibole. But then as pressure and temperature increases, it transforms to an eclogite. And people used to think that eclogite are dry rocks. However, some type of eclogites can have some hydrous mineral, and one of those is lawsonite. So lawsonite has a formula that is really similar to a calcic plagioclase, but it's really different because it can hold around 12 weight % of water. So that is a lot of water that we can put in a single crystal. Now, it is also important to understand lawsonite stability because it can also carry in their structure significant amount of strontium, uranium, thorium, lead, and other rare earth elements on it. Now, the stability of lawsonite and lawsonite eclogites is relatively well constrained by experiments. So I am showing here some experiments from 1994 where they show where lawsonite is stable. And then when we do models, we know that that stability field is really well constrained. Now, according to both experiments and models, lawsonite should be stable at lower temperature conditions at higher pressure. Now, if we superimpose a PT path that represent the stable conditions, PT conditions of active subduction zones. So for example, if you were going to track the PT evolution of a subduction zone, it will be a line like that. So if we just overlap that PT path in the experiments and the models, we can make an easy assumption that lawsonite should be stable in most subduction zones. So it should be a common mineral in the rock record. However, when we look to the rock record, and this has been done, like impressive effort from Donna, kind of compiling what are the different places, the few places on the world where we can find lawsonite eclogites. They are really rare. It's not a common lithology, lawsonite eclogite, in the rock record. So this is usually referred as the lawsonite paradox, meaning that experiments and models tell us that lawsonite eclogite should be common in subduction zones. However, when you go out into the field in different subduction zone terrains, you don't see lawsonite. So why is lawsonite eclogite so rare in the rock record? So the first answers to that question have to do with preservation issues. So essentially, one way to answer that question is saying that lawsonite does not survive exhumation. So here in the left, again, I am showing a PT diagram with lawsonite stability. And then during exhumation, if exhumation is not cold, wet, or rapid, then the lawsonite is going to transform to epidote. And then when you see the rocks in the surface, then you will not see lawsonite because it was not preserved. And most of the lawsonite or lawsonite pseudomorphs are preserved as inclusion in garnet, as an example here that I'm showing from the Colorado Plateau, or a pseudomorph after lawsonite. So this is an aggregate of epidote and white mica crystals from a terrain in Mexico that I interpreted to represent former lawsonite. Now, the question that I wanted to ask in this specific project and potentially answer is whether it is only a matter of preservation. Now, for doing that, I explored actually the opposite, like in what scenarios we can form lawsonite eclogites in the rock record. So for doing that, I couple two different types of modeling techniques. One is geodynamic modeling techniques with the petrological modeling that I was talking before. So a little bit on the geodynamic model. So I did not do these models. So I know there's a big geodynamic research group here. So I just used the models that were available. But we use these thermodynamic models that track the dynamic evolution from subduction initiation all the way to subduction maturity. So we can see that evolution in this cartoon that I did. So here we have a pre-subduction stage that we have two plates, zone of weakness. And then with time, we'll have the onset of subduction. We're going to have an infant subduction zone. And then with time, the decoupling depth is going to evolve. And then with mature subduction, the slab will begin to sink freely into the mantle. Now we can track the PT paths of those different stages. So in infant or infant subduction zones, we experience a hot PT path. So a path characterized by high temperature over pressure ratios. So here in the right, I am showing a temperature pressure diagram with a metamorphic phases in the back. But then in red, I am showing the PT path that a rock will follow in an infant subduction zone. So as you can see, it's relatively hot. Now, if we compare that with a PT path from a mature subduction zone, it's really different. This PT path is characterized by colder conditions. So essentially low temperature over pressure ratios. And then just qualitatively, by looking into the metamorphic phases diagram in the back, you will hope to see different mineral assemblages in those different PT paths. So I couple this observation with phase equilibrium modeling. So phase equilibrium modeling, again, rely on thermodynamic properties of different minerals. So we use input composition that can be a composition of a basalt or an outer basalt or a gabbro or whatever composition do you want. And then you can calculate a pressure temperature diagram that will show you the different stability fields for that specific rock. And then each of these fields represent a different mineral assemblage. So every time that you change from this field to that field, you will have a different mineral assemblage. Now, this tool is really powerful because you can also calculate mineral proportions at any point of that pressure and temperature grid. And then you can extract compositions. We can extract the compositions of garnet, for example, and say something about the PT path. But what I focused for this project was on the proportion of lawsonite and on the amount of water that we expect to see in basaltic rocks that, again, are representative of the oceanic crust during subduction. So we explore those specific things. So these are the results of this project. So here in the left is just a pressure temperature diagram from a normal morph of basalt. I am just highlighting the area where lawsonite is stable. So these colors represent lawsonite proportion in volume percent. Yellow represents a lot of lawsonite, and then darker blues represent less lawsonite. So again, there's nothing new with these calculations to what people have found from experiments and other previous models. So again, the PT line, PT stability of lawsonite is really well constrained. We have that lawsonite proportion increases with pressure at lower temperatures. So from going from 0 all the way to 30, but then it decreases at higher pressure, let's say 3 GPa, it decreases with temperature, okay? And now, these are the PT paths that we use to do our calculations. So again, this is what we expect to see from the dynamic evolution of a single phanerozoic subduction zone evolving from a hot PT path at early stages. So this is 6 million years after subduction initiation. So it's a hot path. And then with time, the PT path will be colder or decrease the temperature over pressure ratios. So a mature subduction zone, so a rock that subducts in a subduction zone 50 million years into its maturity, then it's going to experience that PT path. Now, if we overlap lawsonite stability with those PT paths, we can easily see that in onset of subduction, close to an infant subduction, we do not expect to form lawsonite-bearing rocks. So during the onset of subduction, again, we will form hotter rocks, like amphibolite facies rocks, and that actually matches what we see in the rock record, the high temperature metamorphic soils that are characterized by garnet amphibolites. And then, of course, if we assume any rock that form along that red line, we will not expect to see any lawsonite. Now, the opposite is if we metamorphose a rock in a really mature subduction zone, then that subduction zone will form lawsonite through all its PT evolution. Now, PT paths in the middle will evolve at the beginning through the lawsonite stability field, but then it will go into the epidote stability field. So in these scenarios, if we have exhumation at early stages, then we can potentially preserve lawsonite. However, if we have exhumation at later stages in this PT path, then the rocks that will be exhuming, they will not have lawsonite. Okay, and again, going back to the mature subduction zone, any portion of that PT path where we exhume those rocks will indeed have lawsonite. So that conclusion, those observations remain true from different type of basaltic composition, going from N-morph to an OIB basalt, and even for a gabbroic composition. Now, as you can see from the figure, the gabbro is slightly different, and that's mainly because of the water content that a gabbro can have during subduction. So the stability of lawsonite is also going to be importantly controlled by the water content that we have in our system. Now, what does this is important for the water cycle on Earth? So at the beginning, I was saying, okay, lawsonite is really important because it has a lot of water. So the fact that we have a lot of lawsonite during subduction, then we'll have a lot of water going deep into the mantle. But if we don't have lawsonite, then we need to rethink how we conceive this water recycling on Earth. So again, I run models along those specific PT paths, and I extract the mineral proportions. So this is an output of that type of model. So I call this a model box. So in the x-axis in the bottom, I am showing the temperature increasing from left to right. And then in the upper x-axis, I am showing the pressure. So when we move from left to right, we have increasing PT conditions. And then in the y-axis, I am showing the volume, cumulative volume. So for example, at 450 degrees Celsius, we have that amount of chloride, that amount of epidote, and so on. And then as pressure and temperature increases, we'll have that amount of garnet, and so on. Now, this dashed line tells us how much water we have in that specific rock. And the value of the water can be read in the right side of the y-axis. So here I am showing the water in the hydrous phases in weight %. So for example, at the onset of our models at 400 degrees Celsius and 0.8 GPa, this rock will have around 3 weight % of H2O. Now, as PT increases, then we'll have release of fluid, and then around 1.7 GPa, this rock will have around 1 weight % of water. So as you can see from here, this rock lacks lawsonite. And then at higher PT conditions, this rock has an amphibolite facies mineral assemblage. Now, that will be really different for a rock that subducts 12 million years after subduction initiation. So here we can see that lawsonite is stable at early stages of subduction. Now, that is really important because just by comparison with the previous graph, we can see that this rock at the onset of our models, 400 degrees Celsius and around 1.4 GPa, this rock can carry around 4.5 weight % of H2O. Now, most of that water is going to be in lawsonite. And then after we transition from lawsonite-bearing assemblages to epidote-bearing assemblages, we'll have a strong decrease of water release. So during that transition, we are releasing around 2.5 weight % of H2O. That translates to 64 kilograms of water per each cubic meter of rock that we subduct. So again, that is assuming a density of 1. But that's really cool to think about how much water lawsonite can store in structure. So just for reference, my weight is around 65 kilograms. So 1 cubic meter of rock, that size, will have my weight in H2O. So now if you equate that into the length of, like, for example, the Pacific subduction zone and the thickness of the oceanic crust, you can think how much water is being released just because of lawsonite breakdown. So I think that's really neat to think about. Now, in a subduction zone, a rock that subducts 33 million years after subduction initiation, you can see how lawsonite stability is expanded. And again, the amount of water that is stored in that mineral is really important at the onset of the models, but then we're gonna release most of the water similarly in this transition. Here, we're actually releasing more water than in the previous scenario. And we're releasing that water almost in a small pressure range. So it's like 0.2 or 0.2, 0.4 GPa. So that's a really narrow range of depth where we are releasing 4.4 weight% of H2O. That equates to 144 kilograms of water per each cubic meter of basalt that we are subducting. And again, this is just a basalt. We still need to equate the gabbros and the sediments. And then finally, a rock that is subducting in a mature subduction zone. This is going to be really important for water recycling deep into the mantle, because as you can see from the models, lawsonite remains stable through all the PT evolution, meaning that we can put a lot of water into the mantle in this mineral. So according to these models, we can subduct all the way to 4 GPa, around like 120 kilometers depth. We can put 1 weight% of water in the rock. That is around 34 kilograms of water per each cubic meter. So again, probably it's not as much water in the other scenarios that we are releasing into the mantle wedge, but it's still a lot of water that we can put down deep into the mantle. So that is really important because, again, as I was saying before, it's not just about water. It's also about strontium, uranium, and other rare elements that are in the structure of lawsonite. So just to summarize this first part of the talk, lawsonite is a really important mineral to carry water and trace elements, and its role is going to be crucial for mature subduction zones or subduction zones that can remain stable for a long time. However, the role of lawsonite as a carrier of trace elements and as a water carrier is not probably as important at early stages in the history or in the lifetime of a subduction zone. So I think those are the main key points of this part of the presentation. So if you want to read more about this, this was recently published a few months ago in Geology, so you can download the paper and read more about it, or you can ask me questions. And then we're going to jump to a second part that is not really unrelated. So we're going to be talking about subduction zone metamorphism, but now in the context of earthquake generation. So as I was saying before, dehydration is really important for many things. And one of those things is seismicity. So again, a simplified way to think about it is blue schist has water, then when they transform to eclogites, that fluid is being released, and we have a lot of fluid being released, as I was showing in my previous models. Now we can use petrological modeling to actually know at what depths and how much water is being released. So I've showed this type of diagrams before. This is for a different basaltic composition and for a different PT path. So this is for a cold subduction zone, something similar to a Honshu type in Japan that is commonly used as an example of a cold subduction zone. So here, as I was saying before, that simplified model of blue schist dehydrates and form eclogites stands. So as we can see, these assemblages are blue schist facies assemblages, and then around 3 GPa, they transform to lawsonite eclogite facies rocks. Now, that is really important to understand when this fluid release occurs, because the thermal structure is going to control at what exact depths this fluid is being released. Now, here in the diagram in the right, in the x-axis is the amount of water that we found in the solids normalized to 100%. So here 100% is a rock that is full of water, saturated water. And then as we move from left to right, we are releasing fluid. And then in the y-axis, I am showing depth increasing from the top to the bottom. So going down a subduction zone, we're evolving down. So in a warm subduction zone, something like in Guerrero, Mexico, or in Nankai or Cascadia, we will expect, according to my set of models, that most of the fluid is going to be from the basaltic uppermost portion of the oceanic crust is going to be released at relatively shallow conditions, around 20 kilometer depths. We're going to be releasing around 20, 40% of water here. And then at 60 kilometer depth, the oceanic crust that subducts in a warm subduction zone is going to be mostly dry. Now, the opposite is a cold subduction zone. So in a cold subduction zone, for example, Honshu, because it's a cold subduction zone, we will not reach high enough temperatures to break down hydrous minerals, meaning that we will be able to carry a lot of water deep into the earth. So we will not expect to see any fluid release from the basaltic portion of the oceanic crust all the way until 90 kilometer depth. So 90 kilometer depth, mainly because of lawsonite breakdown, a little bit phengite breakdown, we're going to be releasing most of the water in these greater depths. And what is really important is even at the end of our models around like 100 kilometer depth, in a cold subduction zone, you can still carry a lot of water. So now this has important implications for seismicity because we can relate that fluid release, those depths, with the occurrence of earthquakes or a specific type of earthquakes. So usually people have compared the location of earthquakes with mineral breakdown reactions. And one of school of thought is that that fluid that is being released promote hyperfluid pressures. Now, what is actually a debate in this field is what is the source of those fluids that promote these hyperfluid pressures. So there's two schools of thoughts that can account for the source of fluids. One is that the fluids are traveling from the slab mantle interface or the subduction channel, so it's being released at greater depths, and then they travel through the slab mantle interface up deep, and then in certain portions where they accumulate, that's where you will have the earthquakes. You will increase the pore fluid pressure. Now, the other school of thought is that actually that source of fluid is the same place where these mineral reactions, metamorphic reactions, are occurring. So for this specific project, I compilated different type of episodic tremor and slip earthquakes in Southwest Japan. So I plot those as a function of depth and occurrence. So here we have that most of these earthquakes occur in a range of 20 to 50 kilometer depth. Kilometer depth. And then in the right, I compiled different oceanic compositions from drill cores from basalts, and then run models along those pit paths and see if we have any mineral reactions occurring at those exact depths. So what we found is that actually, yes, we have that most of the fluid that is being released, mainly in this scenario, in this specific subduction zone, is due to chloride breakdown. And that particularly matches well with some of the peaks where we have most of the earthquakes in Nankai. Now, other of the deeper peaks match really well with epidote and amphibole breakdown. Now, this subduction zone is relatively warm. So that's why we have that most of the fluid is being released relatively shallow conditions. Now, I'm going to talk about more in specific another example, again from Mexico, because I'm from Mexico. I'm going to be talking about that earthquake that I was showing before, that is the Puebla Morelos 2017 earthquake. So again, the image in the left is the one that I have been showing before, and this black box shows this inset. So in yellow, I am showing the megathrust earthquakes. So those are the earthquakes that occur close to the trench. And then in purple, I am showing the slow slip events. And here it's important to remember that Cocos is subducting beneath the North Africa plate. Now, a little bit of more context about seismicity in Mexico City. So these two pictures are from the two earthquakes that have destroyed the city, have affected the city the most. So apart from COVID, I think these two events have caused more deaths in all of Mexico City history. So the first in the left is the earthquake that occurred in September 19th, 1985 at 7 a.m. So this earthquake destroyed around 400 buildings and killed 10,000 people. So this was a magnitude 8 earthquake. Now, after, the good thing, what we learned about this earthquake is that after that day, the government put a seismic alarm through all the city. So when the earthquake is measured, it's triggered in the coast, in Acapulco, in Guerrero, in the trench, we get 1 minute until we feel it in the city. So we have this alarm that begin to sound. So something similar to what happened in the morning with this fire alarm. But that alarm will only sound if the earthquake is predicted to be higher than 5. So if it's below 5, we don't really care. But if it's greater than 5, it will begin to sound. The problem is that you don't really know if it's going to be a 5.5, a 7, or a 9. So it's really stressful. But at least we now are able to evacuate the buildings. Now, the second earthquake that I'm going to be talking about is the Puebla Morelos earthquake that happened like a few years ago when I was still a PhD student working in metamorphic rocks. And that's what caught my attention. Like, we really need to understand these things. So it happened in 2017, 32 years apart, but it's really interesting. It happened the exact same day. So a different time. So in 1985, after that day, this day, September 19, there's always earthquake drills. So in schools, in September 19, you will go out and the word is not celebrate, but like, yeah, I don't know what is the word in English, but you know, like we always think about this. But then what was really sad is like in the morning, people went out just for doing this drill, but then return to their offices or school. And then the alarm began to sound again. So they didn't actually knew if it was like something related with the drill or it was actually an earthquake. So it turns out that it was an earthquake. And this earthquake destroyed 250 buildings, but only 400 people died. And that was mainly because we have the seismic alarm and we were able to actually evacuate buildings. So, but what is really interesting is that the magnitudes are really different. So in these 32 years, and even when I was growing up in Mexico City, we have several of 7s earthquakes or 8s. Actually, like 2 weeks before this earthquake, there was an 8.1 earthquake, and it did not destroy the city at all. Like you can feel it, but it did not destroy the city. So there was something really specific about this September 19th earthquake. So some of the explanations can be seen with these figures. So we need to know, see the location. So the location of the epicenter of the 1985 earthquake was in the trench, so it was a mega thrust earthquake, whereas the 2017 occurred deep into the subduction zone, so really few kilometers far from Mexico City. So here, this gray line is showing the position of that figure in the right that shows the thermal structure of the Caucasus plate beneath North America. So I don't know if you can see this really well, but this purple line shows the oceanic plate, the Caucasus plate going down. And then that star shows the location where the earthquake, the 2017 earthquake occurred. So if you can see, it was almost when the slab bends again into the mantle. And then also below the volcanic front. So here the BF is volcanic front. That is essentially the same location as Mexico City. So it occurred just like a few kilometers from Mexico City. And one important thing is that the alarm sound in 2017, but it did, like you did not needed to wait 1 minute to actually feel the shake of the earthquake. It actually occurred like a few seconds after the sound of the alarm. And that was because the epicenter was really close. So the first explanations to explain the origin of this earthquake is based on geophysical evidence suggesting that the location of the earthquake was in the slab mojo of the plate that was subducting in the Caucasus plate. So essentially the limit between the oceanic crust and the mantle. And people speculate that it occurred because of the reactivation of an inherited seafloor fault that was reactivated. So again, here I am showing different seafloor faults. These can be associated with the generation at mid-ocean ridges, or also because of the slab bending. So we can have different type of faults, and then this can subduct. And people think that this can be reactivated. So again, that was one of the speculations about what generated this earthquake. Now, if you see, I trace here the different seafloor faults or fractures that I'm just calling fabrics here. And many of those are actually parallel to the subduction zone. So the eventual subduction of these seafloor fabrics probably reactivated one of those faults that led potentially to that earthquake. But I wanted to go a little bit forward on this project and actually explore if there is any role of metamorphism in this earthquake. So for doing that, again, I did a lot of petrological modeling. I'm not going to go into the detail of these models, but I grabbed different samples that are representative of the lithospheric mantle of the Cocos Plate. There are a few evidence of the mantle rocks there. And I ran models along the PT path that people think is the slab mojo. And then what I want to call your attention is to that red box where the mineral brucite is disappearing, and also a little bit of the mineral antigerite. So what we are looking at that place is a reaction brucite plus antigerite reacts as a function of increase of pressure and temperature into olivine and releases a lot of water. So it turns out that that mineral reaction is actually occurring at the same position where the earthquake occurred. So the way that I model this is considering that my compositional system represent the composition of the mantle localized in those specific seafloor faults. So we can see again that the location for that mineral reaction fluid release matches with the location of the earthquake. So here in the left, I am showing a graph of fluid release as a function of increase of pressure and temperature. And most of that water is being released at that PT condition. And then what is so important is that that fluid release also matches with a slight volume increase of the solids. So we believe that at this exact position, we have that brucite is reacting with antigerite. It's releasing fluid, but it's also leading to a slight increase of volume. And we pose that that leads possibly to the reactivation of these seafloor faults and potentially to the earthquake. Now, what I wanted also to explore is that why these seafloor faults are always subducting and traveling along that PT path, why we don't see this type of earthquakes occur. So for doing that, I explored the degree of serpentinization that the mantle needs in order to see this mineral reaction. So essentially, I consider a scenario where the mantle is fully serpentinized, and then a scenario where it's only 80% serpentinized, 60, 40, and 20. So we found out that you need to have more than 60% of serpentinization to promote the formation of brucite, and therefore to experience the brucite plus antigerite reaction at that depth. So we believe that, again, those seafloor faults or slab bend faults serve as fluid pathways. Fluid can travel through those fractures and then can potentially hydrate not only the oceanic crust, but also some portions of the upper mantle. However, potentially not all of these seafloor faults will be fully hydrated. So in some scenarios, we're gonna have that you're gonna subduct a fault that is not gonna be hydrated at all, whereas in others are gonna be fully hydrated. So that's how we explain the rareness of these type of earthquakes in Guerrero, and also at the same time explain the occurrence of the 2017 earthquake. So again, to repeat the conclusion, we believe that the subduction of one of these hydrated seafloor faults led to the reaction of brucite plus antigerite that promote fluid release, a slight volume increase that promote the reactivation of a fault, and ultimately led to the earthquake, the Puebla Morelos 2017 earthquake. And if you want to read more about this, this paper was published, I think, last year in Geophysical Research Letters. And I think that's all for my talk. So this is just like a big summary saying that subduction controls different important processes, such as water recycling on Earth, seismicity, and that as metamorphic petrologists, we can actually say a lot of things by studying subduction-related rocks, particularly eclogites. So these rocks are from California. So I was really happy because we found an eclogite where no one has found it before. And this is this fresh eclogite, and you see the matrix holding that block. So this is a really fabulous place. So yeah, thank you for listening.
Also want to mention that David is giving a second talk tomorrow at 10 up in the fourth floor seminar room. So want to hear more about subduction?
Any question? Yes.
The solid or the volume increases that solid
Plus fluid. Yeah, solid plus fluid, at least. At the beginning, we were just doing solids, but this is solid plus fluid. Now, that has an important impact on the actual volume change. But what is really tricky, let's see, what is a good figure? Yeah, what is really tricky is that, so when you do this type of modeling, you need to tell your program how much water you have. So if you put a lot of water, like fluid in excess, then this result will vary. So yeah, it's including also fluid. And we treat fluid just as pure H2O. Yeah. Any other question? Yeah.
They showed the two earthquakes and the fluid line two and then
Yes, it was like a mega thrust earthquake. Yeah, somewhere here. Yes. Yeah, so let's see if I have the 2D section. So essentially, like, is a difference in pressure and temperature conditions that you have. So here, close to the trench, just by roughly looking to that isoline, like at those depths, you're expecting conditions of 200 degrees Celsius. So then, however, that will be completely different, at least from the metamorphic petrology perspective in terms of stability of minerals, if you subduct a rock all the way to 550 or like 500 degrees Celsius. So the metamorphic assemblages that you have are going to be really different. And also the depth, well, not the depth, but the amount of water that you are releasing. So yeah, it is different. Now also, like the results that I was showing is for the ultramafic portion of the plate. You are going to expect, you should expect to see a different pattern if you just look to the mafic portion of the Cocos plate. Or even though it's slightly similar PT path, then the compositional system, if it's a basalt versus a gabbro versus a peridotite, is also going to control the type of metamorphic rocks that you will form. Yeah. Any other question? Yes. I don't know if I would like to use the word predict, because yeah, like I will not use the word predict. But I guess that if you had a good estimate of these faults, then the next step will be to see, like, of these fractures of faults, the degree of hydration of those. Now that will be a challenge because you will need to drill all those, and that's probably super expensive. And then you will need to run models, all of those, but potentially, yes, you can say something about what regions are most prone to potentially expect to see these type of earthquakes. Oh, yeah. Yes.
So here you have the pattern that is perpendicular and the other one that is parallel.
Yes. Yeah, in this one.
Yes.
I don't know. Probably that's a good question. I have not thought about it. I think one of the point of the importance of these is that they are parallel to the trench, and therefore, when the slab is bending here, it's like a bending in that specific orientation. So that probably enhance like the slipping of the fault. Like probably you will not expect the same in that side. I don't really know. I will need to think about more carefully about that. But it's a great question.
One answer that would be that what could happen to the because of speed along the interface.
Yeah.
And as you explained, when you were at the end of the plasma region, the activation of the whole
Older, yeah. Yeah, so here, like the question will be like if you're able to reactivate that perpendicular fault. Yeah. Yeah, like again, like if those are like fully hydrated or not, they will have like an impact. Like even though like they do not like reactivate, those metamorphic reactions will still occur. So, yeah. Any other question? Yes.
In your first study, when you're looking at the to mature subduction,
Yes.
Have you considered what difference it would make if like either what age the plate is starting, or like if you've got a plate that's getting older or getting younger, like are you getting closer to a mid-ocean ridge, or are you getting closer to something older? Like what impact that would have?
Yeah, I have not thought about it, but yeah, like definitely, like if you're talking about like different ages of the plate, then at least what I will think initially, like from the petrological modeling side, is that the composition of that oceanic crust will be slightly different. Like people have talked about how seafloor alteration changes with the age of the oceanic crust. So then the input of your oceanic crust, the basalt, will be slightly different, and that can potentially have an impact on lawsonite stability or the stability of epidote or other phases. So that can potentially change, but I don't think that it will have like a really strong effect. At least that's, yeah, thermally, yeah, thermal, like petrologically, yeah, that will be my answer. Thermally, probably, yeah, it will have like it will change definitely the topology of the PT pads that you will get. The questions from people in the Zoom? Okay.
I have one.
Okay.
I mean, some of our geochemical data shows that these are open systems.
Yeah.
So, I think your kind of core system
Mhm.
not only provides really important constraints, but for example, like in the Gavros, we see heat up the water,
Yes, yeah.
some from serpentinite, some from sediments. I don't know how you could.
Yeah, so
quantify it like you have, though.
yeah, so I have done other set of models where instead of just looking into basaltic normal morph compositions, we also integrate different styles of alteration, metasomatism, that will lead you completely different results of what I showed today, and that I'm going to be showing some of those results tomorrow. But yeah, as I was saying, that these models that I am showing, the input is just like a whole rock composition, and that remains the same through all the PT evolution. Now, in some of the models that I have done is open system in terms of water. So the water that's being released is removed from the system, so it cannot be taken again by the system. But yeah, like so calcium, magnesium, silica, that can also travel in these fluids, and it will potentially change the whole rock composition of your system during metamorphism. So the results that you see here will not remain true for in open system composition. So in the geology paper, in the lawsonite paper, we also explore how much the result will change if you have different styles of seafloor alteration or metasomatism affecting the basalts, the gabbros. In some cases, if you have calcium aluminum metasomatism, so that will promote more lawsonite and the stability of lawsonite will be enhanced. Whereas if you have more interaction with an ultramafic rock and your basaltic composition begins to move into a vector towards an ultramafic composition, then you're going to be moving away of lasonite stability. So yeah, it will have a strong impact on the lasonite stability at least. And yeah, in the gabbros, like if you do a model, or if I do a model of a gabbro, same gabbro, but with more water, then you will see exactly the same lasonite stability field than this one. Yeah. So this will expand and will essentially have the same topology as gabbro. That's the result. So, yeah. Good. Yeah. Thank you. Thank you. I'm glad I didn't, like the screen didn't turn green. So. So do I need to log out from Zoom? Is that right? Or stop sharing or?
Yeah.
So stop share. I'm gonna just look at.